Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Teresa Symons with us today. Hey, Teresa.
Hi.
How are you today?
I'm doing well. And you?
On this spring day of April 21, I'm doing well. Things are definitely starting to warm up here in Phoenix. Still cool. It's still not, blazing in Phoenix, but it's getting warmer. Where are you at?
I'm in Rochester, New York.
Okay. Are the tulips coming up? Are there buds on the tree?
They were, and then suddenly today we had snow again. So we're back in snow mode.
It's that tug of war time of year in April. So hopefully soon it'll totally turn the corner and the tulips will come back out. So, what are you doing in Rochester?
I'm a PhD student at the Rochester Institute of Technology. I'm in my 4th year.
Cool.
So I'll be actually graduating next year.
All right. We are getting close. And you're almost Dr. Symons. And that will be awesome. Almost. That'll be awesome. That'll be very good. Yeah. So as long as you're on that, so Teresa, what do you like to do for research?
So I'm using archival data taken by New Horizons to measure the cosmic optical background. Ooh. So the optical extragalactic background light in the universe. Yep. Most people, they hear New Horizons, they instantly think of Pluto, but I'm doing the opposite of that. Basically, I'm using any pictures that are anything but Pluto to measure this really faint background in the universe.
Cool. Cool. And presumably, we'll touch on that a little bit on this very lovely APJ supplement article on super resolution reconstruction of severely undersampled point spread functions using point source stacking and deconvolution. And Teresa, take us away.
So you might be a little confused why I just was talking about New Horizons and cosmic optical background, and now this paper is not that, but it actually secretly is at the end. So we'll bring it back to that work that I'm working on. Cool. But as part of that work, I needed to develop a method for PSF reconstruction in the case of severe undersampling. And this is something that I used both in this project where I'm analyzing the data from New Horizons and also in this paper for simulated Spherex data. So Spherex is the upcoming all sky spectral survey mission. And this is part of the pipeline development for that mission.
Cool. Nice. Yep.
Okay, so I guess we'll just jump right into it.
Yeah, let's go if you like.
So if you want to go to figure 1.
Okay.
Right. So when we're talking about undersampling, we're talking about basically the equivalent of what you see in subpanel C of this figure. So this is just a comparison of if you're changing the pixelization of an image, so it's becoming more pixelated, more undersampled from A to B to C. And then DEF are just a comparison of changing the width of the PSF itself. Mm-hmm. So basically, we're talking about scenarios where your science images look something like C and everything is really pixelated. You can't really pick out the PSF width very easily. So we're talking about reconstructing the actual optical PSF of the instrument from something that looks like C. So if you want to go to figure 3 next.
Okay. Got me with my coffee there. Figure 3. Bam, bam. There you go.
Perfect. Okay, so what we have here is, again, sort of an example of in A, a basic high resolution Gaussian point source. Mm-hmm. And then in B, this is sort of like, again, what you're seeing in your severely undersampled image. And it's just kind of pixelated. And you're like, how will I get from B back to A, which is the true optical PSF of my instrument? So the method that, the algorithm that I developed in this paper uses a basic sort of well-known method called stacking as the sort of the first step. Mm-hmm. Where you're starting with basically B, you've got images full of stars that look like B. And the very first step is you upsample. So going from B to C. So now you have, in this case, you have 100 subpixels now in every pixel. So you are increasing the resolution, and that's what's going to allow you to be able to actually reconstruct the PSF. It gives you this extra sort of subpixel information that can be recombined back into the optical PSF through this method called stacking. And if you don't mind jumping to figure 6 really quick.
Sure.
I can actually show you what stacking sort of looks like. So once you've upsampled the entire image, you basically cut out a little postage stamp around each source, and then you stack them on top of each other. It's exactly what it sounds like. And you take the mean of all of the stamps, and then what you get at the end are these. So this is showing you a stack of 5 sources, and it's kind of, you know, crappy and doesn't really look like anything yet. And then 50 and 500 and 1,000, you can see by at the end, more and more sources, you're recovering basically the PSF that you put into it that you knew was the actual PSF.
Okay.
That's what stacking is.
Cool.
And that's sort of step 1 of the method.
All right.
So if you want to go back up to where we were before.
Yes. Figure 3.
Right. So this is the stacking part of the method. And table 2, I would just want to highlight briefly. When we're talking about, for the first part of the paper, we're talking about simulated Spherex images as a sort of our test case that we're using. This is just giving sort of a perspective on, depending on where you're looking on the sky in terms of galactic coordinates, how many sources are available for you to use. And by available, I mean they're within a certain magnitude range that I'll discuss in a little bit. And then we've got severe source crowding, you know, the lower we get to the galactic plane. So talking about how to select those sources that are isolated from each other, where we can say, okay, this one's here, or they're too close and they're overlapping and then we can't separate them. So talking about using basically just isolated sources that we can identify to be able to make our stack from. So it's just giving a sense of how many are available in any given image that we can use for testing. So if you want to go to figure 4.
Okay, let's do figure 4. Okay.
So what we find is that once we stack, you can see on the left, top left, that's P true. That's our true PSF, our true optical PSF. That's the input. And then on the top right, PS, that's the stack. And you can see it's bigger, it's wider than the original PSF. So we can't just stop with the stack. We have to actually use a deconvolution method to deconvolve out the PSF associated with the pixel gridding itself. And that's what's happening here. So P grid, that's an estimation of the pixel gridding PSF. And in this case, we're deconvolving out using just basic Richardson-Lucy deconvolution. It's an old established method. And you can see in the last panel, then what we have is, it looks, you know, at least to the eye, exactly like P true. So in this case, for basic Gaussian, no noise, no nothing, Richardson-Lucy or RLD is really enough to recover the original PSF. But then things get more complicated. So if we go to figure 5.
So I do have a question. On this third one, or P grid, this is an estimate, right? And so how do you make that estimate, and how would you make a bad estimate or a good estimate?
So this was just developed as just like a very, because we're talking about, we're in this realm where we're upsampled and there's, you know, many subpixels now per pixel. This is just assigning a weight basically to each subpixel, where we say, okay, in the center, that's where the most weight should be, and then decreasing outwards.
Got it.
So it's kind of just like a very, very basic estimation.
Okay, I understand. Okay.
Right, so this method is sufficient for basic sort of cases. But what we found is that the more complicated your PSF is, and the more noise there is, and just all of that complicating stuff, you need a more complicated method. So if you want to go to figure 5.
Okay.
So then the other part of this method that's outlined in this paper is sort of, we're still on deconvolution, on the if there's two steps, there's stacking, there's deconvolution. But now we're making the deconvolution step more complicated so that it can do more. So here we're looking at an algorithm for what's called iterative back projection, which is a method that has been used in image reconstruction, although not necessarily very often in astronomy. It has occasionally been used in astronomy, but it's used much more in like just generic image processing and recovery of like degraded images and things like that. So we're applying this method here where the core of it is still Richardson-Lucy deconvolution. So PS, we're starting from that stack. Then we go to the RLD, that goes some number of times. So we get PRLD, which is what I already showed you. But then for the iterative part of it, so now we're saying that PRLD is like our source. We populated an image where the Richardson-Lucy deconvolution is now the source in every instance. We create a new stack. We stack those up using the same method as before. And then it's sort of this iterative process of calculating the error between the old stack and the new stack. So delta P is just new stack minus old stack. And then it depends where you are in the algorithm. For the first iteration, you subtract the error from just the original stack that you started with. And then in any other iteration, you subtract the error from the previous iteration stack. And then it goes around and around and around again some number of times. And then finally, at the end, what you have is what I'm calling PIBP, which is our best reconstruction of the actual optical PSF. So it's a little more complicated, but it really helps, especially because RLD is somewhat hampered by noise. If there's noise in the image, it kind of can go off the rails really quickly. So this is sort of like an error correcting step that helps to correct for that type of thing.
Question.
So, yeah.
How do you generate the multitude here? How do you generate the stack of PRLDs? I would have thought there would have been, okay, you do some number of iterations and you get a PRLD. So then how do you generate multiple ones?
Oh, okay. So we're creating like a simulated image where instead of in the first simulated image, we put the actual optical PSF in for every source. It's just convolved with the point source. And then in this case, instead of that, we're using just the deconvolved PSF as every point source.
Thanks.
So, something I should have probably made clear was the key part of stacking is really that every source is sampled differently by the gridding itself. You know, it's just tiny little shifts all over the place. The source is never, you know, perfectly centered on a central pixel. And it's really that sort of differences source to source that is allowing us to reconstruct. So, you know, you've got one source over here, one source over there, and then once they have subpixels and you stack them on top of each other, based on their known coordinates from a catalog, that's where you're regenerating that structure.
Yep, got it. Cool.
Okay, so let's see how well this method actually performs. And if we go to figure 7. Actually, this is just about the RLD and not the IVP. So we should go, let's see, let's go to 8 and 9.
8 and 9. Let's do 8 first.
Cool. So this is an example of, again, just for a really basic Gaussian PSF. What you're seeing here is, so what we actually do to test how well this method is working is we do photometry. We do weighted photometry where the reconstructed PSF provides the appropriate kernel weighting for the optimal photometry. So we know what the source fluxes were when we put them in, and then depending on the measurement we get out at the end, we can see how accurately are we able to actually return the photometric flux compared to the expectation. So then this is very important actually, because this is developed for Spherex. Spherex has a requirement for no more than 1% error in photometric flux based on this method. So no more than 1% error can be introduced by anything we're doing here. So you're going to see these plots where I put these sort of gray lines, and the gray lines are just showing that 1% sort of benchmark or guideline that we want to be within. So here we have what the expected flux should have been plotted against the difference between what we measured and what we expected. And you can see So this was for Gaussian PSFs. And this is where we're using only Richardson-Lucy deconvolution. And you can see there's this clear bias. We're getting extra flux. And then on the right, this is just a sampling of, if we repeat this for 50 randomized trials of random field source coordinates, again, you can see we would expect there to be, 0 deviation. But what we're actually getting here is we're seeing, again, this sort of bias to it.
On the positive side, right? This
Yep.
is positively biased. Yeah.
And then, so figure 9 is actually, if we do all this again, but this time we are implementing the full IBP method, you can see the bias disappears, and it's flat. And now, we're not seeing any bias, and we're within 1% error on the flux.
Comfortably.
Right. So it's good. It works in our sort of like most basic test model. Right. But then if we move along, if we jump to figure 14,
okay.
So we do other sort of intermediate tests where we sort of increment and then we add noise and then we're doing other things. But I'm going to skip ahead to where we're looking at actual simulated Spherex Psf. So this is a much more complicated case. You can see on the top left, the Spherex Psf is not Gaussian. It's kind of a really weird shape. Sometimes I call it the hermit crab. It's just like, it's just kind of like this weird alien looking thing. So this is a much more complicated PSF to reconstruct. And also in these simulated images, we are also including noise appropriate to the Spherex instrument. So you can see on the right, the stack. Again, it looks sort of Gaussian, but definitely nothing like the original. And then this is just sort of going through the whole process. So then the bottom left is the Richardson-Lucy deconvolution of the stack, which is a little bit getting back to the original, but still like, not really. And then finally on the bottom right, this is our best reconstruction for the Spherex Psf. And you can see, well, it does look roughly like the shape of the original. It's not getting all these sort of like little tiny details and lobes and things. But what we find is that it actually is good enough to meet our goal, which is no more than 1% error when used for photometry.
Okay.
So if we go to figure 15.
Here we go.
So earlier I mentioned that we have a range of magnitudes that we determined is ideal to use for stacking. And this is specifically for this case. So this was just a test that we did to, if we use, only sources in a certain magnitude bin, how this is sigma delta F is sort of like our figure of merit that we're using to judge the quality of the reconstruction. And we want it to be below 1, that dotted line 1, because that indicates our 1% error in photometric accuracy. And what we determined is, you can see the green bar there, 11 to 15, that was our just ideal range based on testing. Better than any single magnitude band is to use a range of magnitudes that falls in that range. And that gives us our best possible reconstruction. So that was how we figured out what the ideal range of source magnitudes to use was.
Okay.
Let's see.
I'm with you. All right. Signal and noise is given up here. Okay, I'm with you.
Okay. And then, so let's see. Let's go to figure 17.
Okay. Okay, we're going to zoom out a little bit there on that one.
Okay. Yeah, it's a very long figure.
I can blow it up.
The thing about Spherex is it actually has 6 wavelength bands. It has a sort of complicated instrument. So we've been talking about only band 1. That was sort of our test case, was band 1. You can see that's the shape we saw before, but there are actually 6 wavelength bands and we have to test them all. So here, knowing what the appropriate magnitude range of sources to stack on is, we test in all wavelength bands because all the PSFs are very different from each other. And you can see, how good of a reconstruction we're able to return based on just visually how similar they look. And then also the far right is our photometry comparison. Okay. So delta F is that difference in flux that we were talking about before. And this
Right.
is from a set of 50 trials, 50 randomized trials for different fields on the sky. And you can see they're all showing no bias. The mean is right at 0 and fairly low variation from the mean. Definitely always below 1%, which is our goal, no matter the wavelength band that we're talking about.
It's easier to do in this one. Yeah.
Yep.
Ooh.
And then, yeah,
Band here, band 6. What's up with
band 6 is the wild one.
Yeah. What's up with this one? Why is it wilder? Just is.
Well, the method definitely, I've noticed it has a much harder time reconstructing circles. Not circles per se, but you can see it has this ring around the outside of a sort of Gaussian PSF. It has a very hard time with that ring.
Right.
It kind of gets parts of the ring. It doesn't seem to be able to really turn it into a full ring. Okay. So I think that's kind of part of the trouble maybe, is having these extended parts of the PSF that are kind of like off on the edges and disconnected from the main structure.
Right. Also asymmetric as well. Right. It's only on the left side, at least my left on when I'm looking at. It might be on your right. I'm not going to worry about the parity, but there's asymmetry to it as well.
Yeah, definitely. Just the more complicated the structure is, the more difficult time the algorithm has in, recovering all of it.
Still.
But yes, we still meet the goal, which is the important thing.
Yeah.
We still get less than 1% error in our photometry.
Right.
So it's sort of one of those like, how good is good enough type questions. And in this case, this is good enough. So let's see, let's go to figure 18.
Okay.
So again, this is highlighting for the Spherex, in this case, the band 1 PSF, our test case. And for a field, we use a field at the north, all of this I should have said has been a field at the North Galactic Pole. Okay. So the least possible source density that we could have of any field. So basically what we're testing here is we're showing that when we add noise to our images, so A would be, we're adding noise into our stack, into our PSF kernel essentially. And then B would be, we're adding noise in when we're doing, sorry, I don't want to get this wrong, and it's been a long time since I actually looked at this paper.
It's only February 2021, but I get your point.
Well, I've been very busy working on very disparate things from this. So, right, so A is we're adding in, we have noise in our reconstruction. E is sort of like a comparative test where we use a noiseless version of the actual true optical PSF to do the photometry. Okay. But there's noise in our sources still. So basically that shows just that it doesn't, even if you had the perfect PSF and you were able to recover it perfectly, you still have significant error due to noise in the sources themselves. And then C is there's noise in the stack when we make it, but we remove the noise from the sources in the photometry. So this is just sort of demonstrating that there is no significant error due to our methods. It's all due to noise in the image that's causing the problems. It's not, we're not introducing error or significant error in our reconstruction method, which is sort of the goal, is just to show, for this method, we're not increasing the overall error in what Spherex is going to be calculating.
Right, and again, just as a reminder, the gray lines are the 1%.
Yep.
Figure of merit.
So let's see. I think I skipped. Let's go back to 16.
Sure.
I think it's 16.
16. Yep.
So we've shown that this works for all of Spherex's wavelength bands. We showed that it works even including noise in our stack. And in this case, we're showing that we can actually reduce the total number of sources we're using in the stack. So this is fraction of sources. we're just randomly picking a representative sample from what's available to us, and we're decreasing it. And we found that we can still meet our goal, which is that one dotted line, even down to using only 6% of the sources that are available in the stack, which is very important because Spherex has a linear variable filter. So it's different wavelengths across the whole detector array. So you may want to, and probably will have to, compute a PSF not just once for the whole array, but in different areas of the array. Which is common also. Even just detectors, depending on the detector, can have a PSF vary across the detector if it's a large detector. So this is showing that, you know, you can use a subsample of the array and still recover an appropriate PSF that meets the goal.
Nice.
So that's good too.
Yeah, very nice.
And then if we go to, let's see, table 4, which is down,
Okay. Table 4, did I go by? I must have gone by it. Ah, there we go.
And then this is sort of our last Spherex related test. And so we were talking about only using a North Galactic Pole field to do all of these tests. So now we're looking at different fields on the sky, different galactic coordinates, and specifically looking at lowering the galactic latitude to see, can we do this in much more crowded fields? And the answer is we can. Woo. So this is just showing delta F is just the average difference in flux that we get from the measured versus expected value. And then sigma delta F, again, that's just like our figure of merit that we're using. And the important thing to see here is just that there is no significant trend or change in these values. So we're within our 1% error on photometry for all of these fields, even down to galactic latitude of 15 degrees, which is
that's pretty good
because it's a very crowded field.
Yeah, very cool. Very cool.
So I guess then just to bring it back to sort of what I was talking about earlier, if you just up a little bit on figure 19. Oh, sorry, it's up.
That's okay. I'm good.
So I have also developed this method to use when I'm analyzing images taken by New Horizons, and specifically the LORI instrument, the Long Range Reconnaissance Imager on New Horizons, because this is a particularly good instrument for trying to measure the cosmic optical background, which is the science I'm interested in. It's just a very basic kind of optical detector on a telescope, decently sized 20-centimeter telescope. So this is an example of a LORI image, and you can see it is fairly undersampled. Most of the sources just look like a couple of pixels. So this is a test on actual data instead of just simulated, simulated data, even with noise and everything. This has all of the complicated detector effects of a real instrument on a spacecraft. So now we're going to use this, or attempt to use it, to reconstruct LORI's PSF. And this is a case where we don't know the true optical PSF because we don't have access to that information. So we can't do the same kind of test where we know the answer to test to see if we get the right answer. This is just, we get what we get.
This is the real deal here.
So on the right are the results of this test just for this one image. And so we have the stack, and then we have the IBP, which is the final reconstruction. And this is the same image. This is just the top is in a linear scale, and the bottom is just shown in a log scale for comparison. And you can see it's much more noisy. It's much less fine structure is being returned. So this is just due to increasing amounts of noise in the actual LORI images. But what we were able to do from this is, for a set of hundreds of LORI images, we repeated this method, and we were able to compare the PSF width of what we returned to what should be returned, which is about 1.5 arc seconds is the laboratory determined LORI PSF width. And what we noticed is that a lot of our PSFs are significantly extended. You can even see it in this one. It's a little bit oblong when LORI's PSF should probably be, much more Gaussian. And what we found is that we're actually measuring the pointing drift of the spacecraft and the instrument itself. So we were actually able to sort of constrain based on a bunch of PSF we measured compared to the laboratory value. We're seeing about a minimum of 1 arcsecond pointing drift in all our images, which is in line with known values for LORI. So that was sort of like a little extra fun thing that made it into this paper that will probably feature more heavily once I finish my current analysis of lots of LORI data.
Very nice.
But that's one benefit of this method is because we go through this extensive deconvolution process, we are actually able to quantify the pointing drift, which we then could, remove out of the images if we wanted to try to return the optical PSF.
I have a small question. I'm just curious on what the resources are. Once you take your stacked image, how long does it take to return an image on the right? Are we talking, is this a fraction of a second to do this iterative method, or is this minutes per frame, or?
So it would depend how many sources, but at least for the Spherex simulated images that I was doing, which were some number of sources that is given in table 2, about a minute for a fairly crowded frame. So that's sort of the other advantage of this method is, it's not overly complicated. There's no machine learning, anything going on. It's just all very computationally straightforward, and it's very fast. So it does a very decent job. And it's very computationally inexpensive. This is all just done on a personal computer, and it only takes about a minute to analyze an exposure.
And it's embarrassingly parallel. Throw 400 of them up at once on a suitable machine. Very cool. Okay. Very nice. All right. So thank you very much for sharing that lovely piece of work. And so you in the article, and I'll ask it here, sort of future directions. You mentioned a couple times you're going to be applying it to LORI frames, but are there even better algorithms on the horizon? Do you anticipate doing a super resolution reconstruction? And just where do we go with this technology, let's say, over the next couple of years?
So because the bulk of my work is focused on actually trying to measure the optical background with the LORI data, this was sort of just like a side detour in my overall PhD work. So I won't actually be doing any more work, at least for the time being, on PSF reconstruction. Okay. Excuse me. So I have this method and it meets my goals, but certainly there are improvements that could be made, particularly, excuse me, if you start getting into machine learning and that type of thing, there are improvements that could be made in how to automatically pick sources, that type of thing. So there's definitely improvements that can be made, but there's always that balance of computational power needed, time needed.
Versus quality of result, right?
Right.
So what is the topic of your thesis?
Right, so I am hopefully, if all goes well, going to have a definitive absolute photometric measurement of the cosmic optical background, excuse me, taken solely from LORI data taken throughout New Horizons mission lifetime. So that includes anything from while it was on the way to Pluto to after Pluto, and now it's off exploring Kuiper Belt objects. So there's lots of data to mine and use. Indeed.
Cool. Very nice.
And then hopefully, once we have like the measurement of the optical background, then we can compare it to, how bright do we expect it to be based on known galaxy populations, and does it match? Does it agree? Is there some extra diffuse component that is unexplained that we don't know the source of? So then we'll, look into comparing to other measurements and see what we see.
Very nice. Very nice. Well, I look forward to maybe having you back on another one of these when you get that piece of work out. So,
Yes, hopefully.
very cool. That'll do. Thank you very much, everyone. And thank you again, Teresa.
Thank you for having me.
Bye-bye.